about generalized quantifiers. This is the first module on generalized quantifiers. Now, in the previous chapters on quantifier expressions in natural languages, we introduced some natural language fragments that are expressible in the system of logic that is nowadays customary to be called first order predicate logic. Now, in this and the next few modules, we examine a fuller range of quantified expressions in English which have their counterparts in most languages of the world. So the first thing we will note is that first order logic has some inherent limitations as a theory of quantification in natural language in its full generality. Now, there are two kinds of things. One, you can see that quantified noun phrases are not always expressible by means of first order logic. That is one. Number two, standard first order predicate logic also does not take into account the syntax of natural language in a way that's natural. Now, the theory of generalized quantifier, theory of what we call generalized quantifiers, and this is something we will talk about in this chapter, it was first proposed in logic as a way to capture the behavior of a broader class of quantifiers than simply the universal and existential quantifiers. It's again based on an insight of Frege, again the philosopher that we have mentioned. You have seen the name in quite a few places in the previous chapters. He had the insight that quantifiers like existential and universal quantifiers can be viewed as expressing relations between two predicates. And this perspective has far-reaching implications for the treatment of quantification in natural language. As I said before, both from the point of view of what can be expressed in natural language, and two, how a properly compositional theory of the mapping between syntax and semantics would work that first order logic, that languages based on first order logic don't quite do in an insightful way. So let's examine as a first, to see what the point is all about, let's first look at the way quantification is expressed in first order logic and compare it to the way quantification is expressed in natural language. So let's look at the following sentences of English and their first order logic translations. So suppose we consider every donkey sings is the first sentence. The second sentence, some donkey sings. Now, what are their first order logic translations? The first sentence would be translated as, for all x, if p of x, then q of x. The second sentence would be translated as, there exists an x such that p of x and q of x. So the standard way of expressing things in first order logic is by the use of quantifier symbols for all, there exists, and so on. These are the symbols. Then you have symbols for the non-logical constants. So for example, there are symbols for predicates, there are symbols for proper names, and so on. Then you have variables, you have n-place predicate letters. So that's how you get the sentences, the first order logic translations for the English sentences that I just mentioned in 1 and 2. Now, what is the problem with expressing things in this way? Okay. Now, in the following, in the examples that I just gave you, the predicate letter P translates donkey, and the predicate letter Q translates sings. Okay. Now, there's a bunch of problems. One is the syntax of first order logic deviates significantly from the syntax of natural language. In a natural language, quantified expressions are formed by combining a determiner-like expression, every or some, with other nominal constituents to form phrases that can be analyzed as noun phrases. So you have a determiner plus a common noun, maybe some modifiers. Some nouns have arguments and so on, but whatever nominal thing you have. So in a natural language, it's the determiner that combines with a nominal expression to get a noun phrase. Okay, there are some syntactic analyses that analyze these things as determiner phrases or DPs. For our purposes, the distinction is not very crucial. The only thing you need to concentrate on is the fact that the determiner plus the nominal expressions form a unit. Okay. Now, what this means is that in natural language, quantification is what's called restricted. Okay. Whereas in first order logic, quantification is unrestricted. What does this mean? In first order logic, your statements of first order logic are always about all things or some things. In natural language, your statements are typically about all things that satisfy a certain property, some things that satisfy a certain property, and so on. That means the syntax of natural language is very different from the syntax of first order logic. Okay. Now, in first order logic, you have a quantifier symbol, okay, that has a variable in it, and then it binds some variables inside another thing that we call a formula, and then that's the way it operates. So in first order logic, you express generalizations over things. In natural languages, you typically express generalizations about things that satisfy certain properties. Okay. Now, the full class of quantified expressions in a natural language is much larger than those that contain every and some. So, for example, let's take a look at the following sentences of English. No donkey snores. At least 2 donkeys snores. At most 2 donkeys snore. Many donkeys snore. Few donkeys snore. A few donkeys snore. Between 2 and 25 donkeys snore. Most donkeys snore. Now, some of these sentences can in fact be translated into first order logic. So you can see, for example, the sentence no donkey snores can be expressed by saying it is not the case that there exists an x such that P of x and Q of x. Again, P for donkey, Q for snores in this case. At least 2 donkeys snore, for example, can be expressed as there exists a y, there exists an x such that P of x and Q of x and P of y and Q of y and x is not equal to y. Similarly, at most 2 donkeys snore can be expressed as 15 for all x, for all y, for all z, if P of x and Q of x and P of y and Q of y and P of z and Q of z then either x equals y, or y equals z, or x equals z. That means in any circumstance in which you have more than three things, only two at most can satisfy the property of both being donkeys and the property of snoring. Okay? Now, seeing that these are equivalent is indeed somewhat tricky as you look at the example 15, and if you compare this with the English sentence that is translated, it's not immediately obvious. You have to think a little bit to see that the logic translation that I gave, in fact, does translate accurately the English sentence. What this means is that the relationship between a natural language sentence and its first order logic counterpart, as soon as you go past the universally quantified statements and the existentially quantified statements, the relationship between the two are not at all transparent. Okay? So the one major problem is that it's obvious that there is no mechanical process by which you can translate a sentence of English that contains quantifiers into first order logic. So even in simple cases like sentences involving every and some, notice that every donkey snores must be translated as sentence 3 with the connective if then. That's the material implication connective. Whereas the sentence some donkey has to be translated with the conjunction and. Okay? Now there is no principle or algorithm that tells you go from an every statement to a connective, and you go from a universal statement to a material implication and an existential quantifier to a conjunction. Okay? It just so happens that the best way of expressing the meaning of the English sentences happens to be by using these connectives. Okay? In most cases, if you want to give a translation in first order logic of quantified statements in natural language, you basically have to use guesswork. You have to see what is the best way to express things. Okay? So with no, you know it's equivalent to not, there exists. With at most, it gets really complicated, and so on. Okay? So that's the first problem with using the syntax of first order logic as a model for thinking about quantification in natural language. The second and more serious problem is that sentences containing quantifiers like most cannot in principle be translated to formulas of first order logic. Okay? This can be proved mathematically. We won't get into it because it involves knowing a lot more about set theory and logic than we presuppose in this course. But there are people who have proved this. So, for example, there's a paper by the philosopher and mathematician, the logician John Barwise, and the linguist Robin Cooper from 1981, who actually showed that if you take most to mean something like more than half, there really is no way to express the statements 16 and 17. Most Americans who voted for Obama in 2008. More than half of the Americans who voted for Obama in 2008 cannot be translated into a statement of first order logic as long as you are quantifying over people and so on. Okay? Now, we know what does the statement in 17, more than half of the Americans who voted for Obama in 2008 mean. Intuitively, it simply means the following. the number of Americans who voted for Obama is greater than the number of Americans who didn't vote for Obama. Okay? So what Barwise and Cooper showed was that sentences like 16 through 18 cannot be translated into first-order logic in principle unless you also allowed for quantifying oversets. I mean, one of the things, but that's not what we want to do because it seems it's clear that, you know, when we are making these kinds of quantified statements in English, we are not really talking about sets per se. We are really quantifying over ordinary objects, people, things, and so on. So what do we say? What do we do in order to give a satisfactory account of quantified statements as they actually appear in natural language? So this comes about from what we call the theory of generalized quantifiers. Okay. Now, again, there's a slightly different thinking about the semantics of noun phrases, which comes from some remarks by the philosopher Frege. This is the philosopher we've met lots of times before. He's one of the founders of modern logic, and many of his insights are crucial to the kind of semantic theory we are looking at. Okay. So while Frege's works are often seen as the precursor of modern logic, the way it was formalized by people like Whitehead and Bertrand Russell and so on, Frege also remarked in passing that quantifier expressions of semantically these correspond more to what we call determiners in the syntax of natural language. Okay. What he remarked at various points was that you could see quantifiers like every and some as expressing second-order relations between what he called concepts. Okay, what Frege meant by the term concept is roughly what we mean when we use the word predicate. Okay, so for Frege, a quantifier like every and some expresses a second-order relation between two predicates. Now, to see what this means, think about statements involving every and some. So whenever we say every donkey snores, if you look at it in this particular way, you can see that it expresses a certain relation between the predicate donkey and the predicate snores. Basically, anytime you say that every donkey snores, you are saying that the extension of the predicate donkey is a subset of the extension of the predicate snores. Similarly, some donkey snores simply means that the extension of the predicate donkey overlaps with the extension of the predicate snores, and so on. Now, in mathematical terms, if you use a little bit of set theory, something we have seen, some of which we have seen so far, what this means is the following. Every A is a B if and only if A is a subset of B. Some A is a B is true if and only if A intersection B is not the empty set. Okay? So, the meanings of the quantified expressions, every, some, and all of the rest can similarly be elucidated in set theoretic terminology as follows if we take Frege's idea that these expressions are second-order relations between predicate extensions, okay, and so on. Okay, so what can we say? So here's what we have. Let's look at the following formulas. Every A is a B is true if and only if A is a subset of B. Some A's are B's is true if and only if A intersection B is not the empty set. No A's or B's is true if and only if A intersection B is the empty set. At least n A's or B's, where n is any number, so 2, 3, 4, what have you, is true if and only if the number of things or the cardinality of the set A intersection B is greater than or equal to n. At most n A's or B's is true if and only if the cardinality of A intersection B is less than equal to n. Exactly n A's or B's is true if and only if the intersection of A intersection B, if the cardinality of A intersection B equals n. Most A's or B's is true if and only if the cardinality of A intersection B is greater than the cardinality of A minus B. The A is a B, where A is the denotation of a predicate that happens to be the that's the extension of a singular, of the restriction of a singular definite description. We say that the A is a B if and only if A is a subset of B and the cardinality of A equals 1. Okay, so the basically means every A is a B's, and by the way, there is exactly one A. Similarly, both A's or B's is true if and only if A is a subset of B and the cardinality of A equals 2. The n A's or B's is true if and only if A is a subset of B and the cardinality of A is simply n. Similarly, the vague quantifiers like many, few, and a few can similarly be defined as follows. Many A's or B's is true if and only if the cardinality of A intersection B is greater than or equal to k, where k is a contextually determined large number. Few A's or B's is true if and only if the cardinality of A intersection B is less than or equal to k, where k is a contextually determined small number. A few A's or B's is true if and only if the cardinality of A intersection B is greater than or equal to k, where k is a contextually determined small number. Okay. Now, the right-hand side of the equivalencies given above are determined by the meanings of the quantifiers on the left-hand side. Okay. And this provides a perspective on quantifiers that's in some respects significantly different from what we are familiar with from first-order logic. Okay. Now, a related issue is the question of the compositional interpretation of quantified statements. In our previous treatment of every and some, we used the rules of semantic interpretation that were syncategorematic. So what we did was we said every B indexed with an I followed by an S is true if and only if some condition obtains. Now, rules of this kind are not strictly compositional in the sense that we didn't assign any values to the determiners every and some. And this is a slight problem. Okay, it's a slight problem because it violates one thing that we might call strict compositionality. It's better to have a theory that's strictly compositional in the sense that at any given point you assign semantic values to linguistic expressions, and then you compute the value of the mother node that contains these two immediately dominated nodes, and you let your semantic interpretation keep going like this. Okay. To see the point, consider the noun phrase every donkey in the sentence every donkey snores. Okay. We know that the verb phrase snores is a one-place predicate and so belongs to the semantic type et. The entire sentence, of course, can be true or false, so it's of type T. Now, in previous chapters, we have seen that proper names like John are of type E, and so the semantic value of John can apply as an argument to the function denoted by snores, as the types are the right ones that allow for a correct application of the function application rule. However, we know that a noun phrase like every donkey cannot be of type E, as they don't denote things. That means if we want the rule of function application to apply, every donkey must be a function that takes the predicate, as must have a semantic value that represents a function that takes the semantic value of a predicate as its argument and gives a truth value as a result. This means that every donkey must have a semantic type ET. What kind of semantic value must every donkey have? Well, a simple way of looking at it is the following. We say that every donkey snores is true if and only if snores is in the denotation of every donkey. Okay, you can note that snores is in every donkey if and only if the extension of donkey is a subset of the set of snores. We know that we just saw that is what the meaning of every is. From these two statements, we conclude that the semantic value of every donkey must be the set of all x's that are subsets of my universe of discourse, such that the extension of the predicate donkeys is a subset of the set X, where U is my universe of things. Okay. Similarly, you can see that some donkeys will be the set of all x's, such that the extension of donkeys intersected with X is not the empty set, and so on. You can take a look at this for the other noun phrases that have the other quantificational determiners that I just mentioned. Okay. Now, once we have this, what can we say about? Now, so far we use the term quantifier to mean the expressions every and some and so on, and that's the standard practice in logic. However, when we do linguistic semantics, we prefer to use the term generalized quantifiers for the denotation of noun phrases. Okay, there are various reasons for this. It's because what you call quantifier in logic is syntactically a determiner. So what I have given you so far are what the denotations for quantified noun phrases in natural language look like, and those are what we call generalized quantifiers. Now, once we have this, you might call expressions like every and some as basically what you might call them as semantic determiners. What is a semantic determiner? What does a semantic determiner do? We have seen that a noun phrase can be taken to have the semantic type ETT. What is a semantic determiner? A semantic determiner combines with a predicate, namely something of type ET, and gives you something of type ETT. That means your semantic determiners like every, some, no, at least n, and so on, then must have the semantic type of ET, ETT. Okay. What this means is what you see in 44 through 50. Every applied to y must give you the set of all x's that are subsets of u, such that y is a subset of x. Similarly for some, no, at least, and so on. Okay, so once we do this, we get a system that that better reflects the semantics of quantified statements as they appear in natural language and does justice to the syntax of natural language.